Hello, good morning. So we are starting our lectures now, please. I'm sure most of you may be seeing me for the first time. Are we all together? My name is Dr. B. Dan-asabe. So I'll be taking you through Engineering Metallurgy 1, MCE 309. Are we all together, please, class? So please, those of you that have background noises, please try and reduce them. So these are the topics we are going to be treating today. Look at these items. Please, who is with that background noise, please? If you know you have a bad background noise, please, you should mute yourself, please. It's only when you have a question, I expect to have a conversation with you, please. So we shall be looking at, this is the outline we are going to be looking at. We'll be looking at today introduction to metallurgy. We shall be looking at extraction and refining of metals, and then purification. And lastly, we look at history of metallurgical processes in Nigeria. Are we all together, please? These are the reference materials for this course. You have three textbooks here. So we start with introduction to excuse me, to metallurgy. So what is metallurgy basically? Even from the word metallurgy, you can hear there is metal. So it's the science and technology of metals. So the concept of metallurgy is derived from physics, chemistry, and crystallography. We all know what physics is. Physical study of physical things, mathematical analysis of them. We all know chemistry, elements, chemicals, and crystallography is the study of microstructure, right? Microstructure of metals and other elements. The microstructure at either the macro or the micro or the nano level, right? When you say nano level, you are looking at a very, very much minute level at 10 to the power of minus 9 meters. And when you talk of micro at 10 to the power of minus 6, and when you talk of micro, that's milli at 10 to the power of minus 3, or even larger than that. So metallurgy is a domain of material science and engineering that studies physical and chemical behavior of metallic elements, their alloys, and intermetallics. So we are going to see what all these are. We already know metallic elements. Alloys, when you have two metals joined together, right, physically combined together to produce a much superior material, we call that alloy. And intermetallics is also an alloy, but has higher resistance to, or has higher resistance, has better thermal properties at higher temperature. So metallurgical field may be divided into two large groups. We have the process or extractive metallurgy, and we have the physical metallurgy. So in today's lecture, we are going to be, we concentrate ourselves on extractive or process metallurgy. Here it deals with the obtaining of ores, mining of ores, and their extraction and refining. And physical metallurgy deals with the chemical, mechanical, and thermal properties of these metals. So you can see chemical, mechanical, thermal, and others. So mechanical encompasses a lot, drawing, stamping, forming, and many other things, the properties of these metals. So let's start with extraction and refining of metals. Are we all together, class? Are we following, please? Uh-huh. So the first here is extraction and refining of metals. Metals occur in nature in free as well as in combined form. So there are two ways, either in free form or in combined form. So an example of metals in free form are what? Who can give me an example of metals? Metals that don't require any special refining. They are freely, you get them in their pure form. This is what we mean free in nature. Example is gold. When you get gold, you cannot, you cannot refine gold. What I mean is that gold is found freely, but like other metals like aluminium, copper, sometimes before copper used to be found freely. When we say freely, we are talking of in pure form. But now some of the coppers you don't find them freely in the atmosphere. Even though when it was found before, it was still with contamination with other elements. Maybe you get like 92 or 95% copper. But now most of those ones are not available. You have to what? You have to follow a process of what? Purifying them, refining and purifying them, right? So only few metals exist in their free form. Example is gold and other rare metals, palladium, but they are difficult to find. But those ones that are found in combined form, they are not found in free in their pure form because they are highly what? They are highly electropositive, and so they don't exist. It's difficult to find them in free form, but in combined form. So it means you have to follow a process of what? Extraction. Naturally occurring material in which metal or its compound occur is called what? Mineral. So a mineral from which a metal can be extracted economically is called an ore. So when we say an ore is an economic what? Mineral that we use day in, day out. An example is steel, aluminium, copper. Though these are not the minerals, but these are the final purified products. These metals I just mentioned, they are what? They are found in combined form. So since they are found in combined form, how do you get them in their pure form? You have to what? Follow a process of what? Refining, extraction, and refining them. This is what we call concentration. So we are going to look at. So these are some of the examples of minerals, of ores, economic ores. Example are magnetite. This is an iron ore. It means it's a mineral or ore that you can be able to, that you get metal in iron in predominant quantity. Next one is another mineral is what, or another ore is chalcopyrite. And this chalcopyrite is what? Is a compound of sulfide, and it is called chalcopyrite, copper iron sulfide. And this is for what? For refining copper. It means copper is in more predominant composition. We have the carbonates, calcium, magnesium. We call this dolomite. We have smithstone for zinc. If you want to refine zinc, you can't find zinc freely. You can't find calcium freely. We have also canalite, potassium, magnesium, chloride. In this case, you can either get magnesium in more quantity or potassium. We have others, beryl, calamine. So these are some of the predominant ores. Are we together, please? Hello, class. Ores are invariably found in nature in contact with rocky materials. So these ores, you don't find them freely because they are what? They are those that are found in combined form. So because they are not pure, you can't find them freely. It means there are what? Impurities within them. So the earthly impurities, they are impurities that are intrinsic. It means they are not earthly, other metallic impurities, but and then there are other impurities that are what? There are earthly impurities because they are found in the earth crust. They must be combined with also what? With the rocky materials. So in this case, the impurities we call it what? Ganj or matrix. So I normally ask this question always in my quizzes. So the impurities, the earthly impurities accompanying these ores are called what? Ganj or matrix. So let's look at the method of extraction of these metals. The choice of this process, these are some of the processes 1 to 5, but they are not definite. It means for some metal, you will have to follow, while some metals are suitable for other methods, right? But these are general methods that you can use for extraction of metals. But it's not the same for all the ores, right? Each ore is specific for its own. So let's look at them: crushing, pulverization, concentration, calcination. Then let's look at one after the other, these 5. And lastly is the purification. In this case, we remove most of the impurities from 1 to the, we may get rid of different impurities from 1, 2, 3, 4. But the 5 is the final purification, where you can get almost 99 or 100% of the what? Of the metal. So let's start with the first one. And the big lumps, because it's gotten from the earth crust, extracted by excavators, they have to be what? Crushed. Some of these also have to be crushed using jaw crushers, and then grinders to reduce much of its sizes. The crushed pebbles, pieces of ore, are then pulverized in a stamp mill, so they are made into powder. Right, this is the first step. So I can have the powdery form of the ore. The next step is concentration or dressing. Here, concentration means increasing the concentration of the metal while decreasing the what? While removing the impurity. So the process of removing the ganj, the earthly impurities from the powdered ore, is called what? Concentration. So removing the earthly impurities. There are several methods for concentrating the ore, right? The choice depends on the type of what, or the nature of the ore. So we have gravity separation, magnetic separation, flotation, and chemical what? Method. So let's look at A to D. So here is like you have a slope. In this case, if, for example, for iron that is expected to be extracted in large quantities, um, suitably this is close to a river, whereby you can be able to, it has a slanting and vibrating slope, whereby in this case the principle is density here. It's expected, for example, iron is much heavier, about 7.8 grams per cm cube, the density, while most of these earthly impurities, they have about 3, density of 3 grams per cm cube. So here this is slanting and vibrating, so the lighter ores are washed away, leaving behind the what? The heavy ore. So in this case, it's not meant for lighter metals like aluminium, because aluminium is about 2.7 grams per cm cube. So it may not be suitable. It's suitable for what? Heavier what? Metals that have high density, as compared with the earthly impurities. Most earthly impurities range from 2 to about 3 or maximum of 4 grams per cm cube, their densities. So in this case, they can be separated. Are we together, please? While the denser element metal is left behind. Hello, class? Are we following, please? The next one is magnetic separation. In this case, use a kind of this magnetic roller. In this case, it's suitable for what? Magnetic ores. I think magnetic ores examples are iron and chromium. Is it chromium or manganese? So these are some example of, it's not suitable for all, because after metals are magnetic. So in this case, as you pour in the powdered ore on top of the roller's conveyor that is moving, here it separates the what? The earthly materials. There is non-magnetic, so it will just flow, while the ore, the metal which is magnetic, clinges onto the what? Attaches itself onto the roller, and then is separated. So in this way, you can separate them, the ganj and then your metal. Is it clear? So this is suitable for what? Pyrolusite and chromite ores, right? Where here you can get manganese, and then here you can either get iron or chromium. So next is flotation. In this case, we look at affinity to air and affinity to water. So this is suitable for sulfide ores, for example, that of copper. The principle here is the metal that has affinity to air will go to the top. Here you have compressed air together with what? With pine oil. So this is mixed all together. The mixture of the ore, the powdered ore is poured in. The ore has, in this case, the ore has affinity to air. It moves up, while the earthly impurities, the ganj, moves down because it has affinity to water. So the air bubbles will carry the ore to the top and they can be separated. This principle is based on affinity to air. It will follow, air will carry it up, and the other component, the ganj, that has affinity to water, will go down. Next is chemical method. Here is adding sodium hydroxide to form a precipitate of sodium. So in this case, an example of this ore is aluminum oxide, aluminum ore. In this case, you add sodium hydroxide, it forms a precipitate. The sodium aluminate is diluted with water to obtain a precipitate of aluminum. So it's further what? Water is added further to have this, and then finally you heat to have aluminum, the more concentrated. It means here you have more concentrated aluminum as compared with the initial. Yeah, though you can see it's the same element configuration, but here we expect that there are more. Here there are more impurities as compared here. So the third stage now is calcination or roasting. So after dressing, after increasing the concentration of the metal you are interested, and removing the earthly impurities, that's in the second stage. Then the next stage is calcination or roasting. So there are two different things, but they are similar. So in this case, after each of these, either each of this process, the metal is converted to what? Metallic oxide. So calcination involves heating in limited supply of air. Both is heating in air. In calcination is limited supply of air, while in roasting is in open atmosphere, in free supply of air. So in both cases, you are not supposed to heat to the melting point of the iron, right? Because of the metal. I won't say iron. Iron is just an example of metal. So when you heat below the melting temperature, most of the impurities will go away, right? Will be removed. But the major difference is calcination is in limited supply of air. Some of the impurities can be moisture, water of hydration, and volatile substances, gaseous volatile substances will go away, and also in roasting. The following changes take place during roasting: drying of the ore. So here the ore is dried, removal of volatile impurities, and conversion of sulfide ores into what? Oxide. So in both cases, the metal is oxidized, right? In three. So though in the same way, impurities are what? Are removed. So the next stage now is because in the third stage now, the metal is oxidized, then it means you have to reduce it, because we don't want to have metallic oxide as our metal. We want a pure metal. So in this case, this process, in the previous process, the metal becomes oxidized. So in this case, you have to reduce it, remove the oxide, right? The first one here is for reduction is smelting, and second one is reduction by other methods. In this case, smelting is a process in which the oxide ore in molten state, so it's heated to molten form, and then reduced by a reducer. So most reducers are what? Carbon. You can use carbon as a reducer. You have other reducing agents, and there's also self-reduction. And then in the second method, where you cannot achieve reduction by A, then you can use by B. So basically, it's just removing the oxide in this process. So we look at the different A, B, C, different types of reduction or reducing agents. Are we all together, please? Class? So let's start with smelting. Smelting basically is using carbon as a reducer. You know, from an elementary level, carbon is a good reducer of most metallic oxide. This method is used for isolation of the iron, tin. So these are examples of metals that can be reduced by carbon. when you add carbon here with an iron oxide, so this is an example of illustration of an, though it may not be complete, but it just give you an idea of the ore. So when you add carbon onto it, you have iron. It's reduced to what? Pure iron. And then you have carbon monoxide. And finally, the process continues, you'll have finally iron reduced. And when you have tin oxide, it means here is the ore. Tin oxide is the ore. It can be reduced by carbon. Similarly, zinc oxide, a zinc ore that has been what? Calcinated or roasted can also be reduced by what? Carbon. So let's look at a concept of flux. Although the ore has been concentrated in earlier step, it is still contaminated. There are still, in the second step, you release most of the gangue, but there are still some that are still left behind, right? So for example, if you are trying to purify iron from its ore, in this case, there's what we call a flux. So basically, a flux is added to smelting to the blast foil in a blast furnace in smelting of iron. For example, in smelting of iron, it means iron is heated. There are still more impurities. So how do you remove that impurities? You add what we call flux. So there are two types of flux. For example, for iron, the expected flux is what? Is an acidic. Sorry, the expected impurity is called acidic gangue. So it means the best flux to add is calcium oxide, and this calcium oxide is gotten from what? Limestone. So you add calcium oxide onto the molten iron, and so it will combine with the impurity in there to form what? Slag. So basically, slag is used to what? Remove impurity. Okay. So when you add slag onto the molten iron, it will form what we call slag. When you add, flux, it will react with the impurity in the iron to form slag, and this slag is not miscible with the what? With the iron, so they can be separated. Usually in the blast furnace, the iron is heavier, it goes down, while the slag is at top. It means the remaining impurity in the iron is removed by adding flux, which forms this compound slag. We also have another type of impurity, but in other, this thing is called basic gangue. So in this case, we use basic flux, and in some cases, you may decide to use acidic flux depending on the type of metal. In this case, if the iron ore, the metal you're trying to purify is copper, in most cases, we expect copper to have basic impurity, which is called basic gangue, iron oxide, and this can be removed using what? Acidic flux, silicon oxide, to form this slag. In most cases, the slag and the metal expected, they are not miscible, and thus they can be separated. Next, we have what we call self-reduction. Self-reduction is just heating the ore in what? Air. Sorry, the next are other reducing agents. We have aluminum as reducer. When you have chromium or manganese ore also can be reduced by aluminum. Magnesium can also be a reducer apart from carbon. So you have titanium chloride ore can be reduced by magnesium. Titanium oxide ore can be reduced by sodium. These are other reducing agents: aluminum, magnesium, sodium, and also hydrogen. I'm sure you can see hydrogen. And then we have also self-reduction. Self-reduction means you're not adding anything, it's just heating in open air in oxygen. Air, there is high composition of oxygen in air. So when you have the ore here, you heat in oxygen, it produces what? From the sulfide ore, it produces copper oxide, and continuously you have your copper reduced. Also, when you have mercury ore, cinnabar, heated in oxygen, finally you can get your hydrogen, your mercury. I hope you can see my arrow. And when you have lead ore in oxygen, you can have finally what? Lead. After a process of what? Reactions, you can finally have lead here, pure lead. Then reduction by other methods. Here, if it cannot be reduced by other reducing agent and carbon, you can use this. Reduction by precipitation, by adding sodium cyanide and you can see with the following reactions, you can finally have what? Silver. Assuming you have silver, the ore is an silver concentrated ore. And you can also have by electrolysis reduction, sodium chloride at the cathode, sodium is reduced, while at the anode, chlorine is ejected as what? Gas. So in this case, you can use sodium cyanide whenever, you can use electrolysis also to finally purify metal. In this case, the sodium is the metal, isn't it? Um, while sodium is reduced, while chlorine is ejected. So finally, we look at purification. Are we together? We have purification of these what? Of these metals, right? We have looked at the process, and here we want to look at the final purification. So in this case, you can use liquidation, pooling, distillation, electrolytic what? Refining, or finally zone refining. So in all the process we've done, there may still be what? Some impurities. So you can use this to finally remove some of these impurities. So let's start with the first one here, liquidation. We're looking at metals that melt easily fusible metals that have lower melting temperatures like tin and lead. Lead has about 300 plus, while tin has about 270 plus. So in this case, it means as you heat, here you expect that the impurity has higher melting temperature. So it means here this reverberating hurt with slope, it means here the metal melts easily and is separated here, leaving behind the impurity. Are we together, please? Metals with lower melting temperatures is good for liquidation because they melt faster easily and leaving behind the impurity. Next, we have pooling. Here, it involves stirring with a hydrocarbon stick, a green stick. This green stick is a source of carbon. Carbon is a reducer. So as you add onto the molten metal, it's carbon to react with oxygen to form carbon. Right? The carbon in the green stick react with the oxide to form what? To eject carbon dioxide out. So it continues to remove the oxide, and then what is left behind is the metal. Example is copper and tin that are in the impure form of copper oxide or tin oxide are refined by this method. You continue using these green logs so that it can eject what? Carbon dioxide. I think in some of the previous reduction by carbon, this is similar to reduction by carbon, right? Next is distillation. Here, when we say volatile metals that turn into vapor easily, right, can be purified by this method. Here, volatile metals like zinc and mercury are purified by this method because they turn into vapor easily at a much lower temperature. This is based in difference between boiling point of the pure metal and impurities. It means impurities have much longer to become into what? To even melt, right? So in this case, the pure metal turns into vapor easily, and then it is condensed here in this stage, and then finally it is vaporized and then condensed, and finally it is collected on this as distillate, while leaving behind the impure non-volatile impurity. Are we together, please, class? Then we have electrolytic refining. In this case, large number of metals like copper, zinc, silver, excuse me, and you can also refine metals by electrolysis. One of the best way, the most purest form to get pure metal. So a block of the impure metal is made as the anode. So in this case, block of the impure metal is made as the anode, and a tin. So in this case, you go and get a tin sheet of the pure metal as the cathode. and you have a suitable what? Electrolyte. So it means from the anodes, the pure metal, the impure anode with the metal, it means the metal will leave the anode here, continuously be dissociate from the anode, decomposes from the anode, and then attaches itself on the what? On the pure cathode. So the cathode begins to what? Increase in size continuously till all the metal here in the anode is removed, leaving behind the what? The impurity. So these are some of the metals that can be purified by this method. And lastly, we have what we call zone refining. Are we together, class? Hello, class. Hello, are we together, please? Okay, when I'm done with this, I will answer Afigwa's question, please. So in zone refining here, here we look at the differences in their what? Difference in the here is based on the principle that impurities are more soluble in the melt form than in the solid form, right? So in this case, you heat the metal to to some temperature, to the crystallization temperature, so that you can be able to move away the impurity and leaving behind the pure metal, because impurities are more soluble in the molten form. So as you heat the metal, in this case, the metal will have much higher melting temperature, and then the impurities will melt earlier, right? So as you heat the metal, below the melting temperature of the metal, the impurities must have become molten, isn't it? And so you can use this, there's this heater, you can see this circular mobile heater can be used to move away the impurity. So as you move away the impurity, because they are molten, you are leaving behind the pure recrystallized metal, and the metal later recrystallizes because it's a bit heated, and it will finally you leave behind the pure metal. So in this case, as you move away the heater, you're moving away the impurity that is molten, leaving behind the what? The pure metal, which finally what cools down, or what we say we call recrystallizes. At the end of this, at the end, so it means at the right end there will be more of impurity, while at the left end there will be more of the pure metal. So in this case, when you have reached close to the end, you can cut off. It means leaving pure metal behind with the from as the left, while the impurity together will still the metal on the right, while the impure metal at the right. So we have come to the end of today's lecture. Though there is one topic left, and we shall still look at that.